Hello everyone, I am Dassanayake, currently from University of Sri Lanka. I was formerly a postdoc at University of Plymouth, UK. My co-authors are Professor Alison Raby, Dr. Alessandro Antonini, Dr. Ed Ransley, Dr. Kieran Monk, and Professor Deborah Greaves. This project was conducted with collaboration of several UK universities and lighthouse authorities from UK and Ireland. First, I will give a brief introduction to the project, which will be followed by experimental model setup, and finally I will conclude my presentation with some results. Estimation of impulsive wave loading on cylinder upon shoals poses a unique challenge to marine structural engineers. We believe this research study will enhance our understanding of the loading and will support us to design the structure shown below. This project was conducted as part of the broad STORMLAM project. STORMLAM stands for Structural Behavior of Rock-Mounted Lighthouses at the Mercy of Impulsive Wave. Main objective was to study resilience of 19th century rock-mounted lighthouses. Main aspects include on-site investigation, scaled hydrodynamic model test, CFD modeling, structure analysis using finite element modeling, discrete element modeling, and limit analysis. The figure to right shows 7 lighthouses studied under this project, and Wolf Rock is encircled with red color. The Trinity House, one of the lighthouse authorities, performed bathymetric survey to survey the Wolf Rock, and the topographic survey was undertaken by University of Plymouth. As you can see from the rightmost images, Wolf Rock has different slopes for different directions. A 3D model of the lighthouse, rock pinnacle, and the boat landing was developed using the aerial images taken during the topographic survey. The two plan views compare the rock geometry shown in the historical drawings and also the contour lines extracted from the current 3D model. As you can see, there's a substantial difference between what is presented in the historical drawings and what we found during the survey. After carefully analyzing the wave statistics and the rock slopes, it was decided to perform laboratory tests for the sector between 270 and 300 degrees from north that represent approximately 50% of the dominant wave directional sector. And the design water level was plus 6.9 meter CD that represent a 1 in 100 year storm that could come in 2067, which is our time horizon. Based on the hindcast wave data sets, we came up with wave heights which has a return period of 250 years for 2017 and also for 2067. So for 2067 we are expecting H 0.1% to be 25 meters. Ocean basin tests were carried out in the deep basin of University of Plymouth, which is approximately 35 meter long, 15.5 meter wide and 3 meter deep. The main objective were to generate a comprehensive data set for calibration and validation of CFD simulation, develop a more realistic force time series that can be used as an input for our structural dynamic model, and also to generate some lab tests to compare with field measurements using stereo imaging system. The model scale was 1 in 40, which resulted in a lighthouse approximately 1 meter tall. The lighthouse was 3D printed, and then the bathymetry was made from wood. We had to truncate the bathymetry, and so we constructed only between -48 to 0. The ocean basin in University of Plymouth has a movable floor, which can be raised above the water level to have dry construction. Then we can lower it to the desired water depth, and we can achieve up to 3 meter water depth. The figure towards the left shows the instrumentation inside the lighthouse. The lighthouse is equipped with 12 pressure sensors, 2 accelerometers, and 1 6-axis load cell. In addition, the wave basin is equipped with 12 resistance type wave gauges to measure the water surface elevation, and also we used calibrated high-speed camera and digital video cameras to measure wave runup, and also wave transformation on the reef. In the ocean basin, sediments are not allowed. Therefore, we could not go with the conventional construction methods of creating the bathymetry. We had to find an innovative way of doing it. So we used water jet cut profiles to create the skeleton of the bathymetry, and then it was covered by thin marine grade wooden plywoods. Figure C shows the internal structure to support the lighthouse, which is constructed with aluminium frames to provide a stiff construction to hold the lighthouse structure firmly, and also that help us to measure the wave loading. In order to improve the accuracy of the rock pinnacle, 18 mm thick horizontal wooden profile were used from 0 chart datum onwards. Just to recall, our design water level was plus 6.9 chart datum. The steps between profiles were then smoothened using wooden filler and finally coated with a water-resistant resin. The lighthouse was 3D printed as 11 separate components, and then they put together using aluminum column. Printing the lighthouse as several components reduces the risk of reprinting the entire lighthouse if something goes wrong during the printing process. Figure B shows a 6-axis load cell, and the entire lighthouse load came on top of this load cell. Figure C shows the pressure sensors, and D shows the accelerometers. Figure E shows the marks from the lighthouse, which was used for motion tracking using advanced camera system. To provide a perspective of the scale, Dr. Kiran Monk, the main figure behind this entire construction, is standing next to the lighthouse model. The other two photos were captured during the model tests. This video shows the model testing. A wave generator consists of 20 separate paddles generating waves, which then approach to the wolf rock model. As you can see now, here we have some preliminary results. For the comparison, we are using estimated impact force to create an uplift or opening up the masonry courses. This force is only valid if the wave is hitting the area proposed by Wincan-Amorasi method. Figure A shows the theoretical impact area derived from Wincan-Amorasi formula for 2017 and 2067. And the graph shows the force time series of theoretical force, which lasts only 0.7 seconds. Figure B shows force time series from the physical modeling, which shows the force goes much higher than this theoretical uplift force, and also the duration during when it goes above the threshold is approximately 50 times larger than the theoretical duration. However, later we found that it is not critical because the impact area is not as same as the theory proposed. The impact area is much lower than that. Therefore, the load required for uplifting or opening up the courses is much higher than this calculated theoretical force. The plots here comparatively shows results from regular wave test and focused wave group tests. Focused wave groups enable us to reproduce larger waves up to significant wave height of 12.85 meters. Also, with the focused wave, the breaker point was much closer to the structure, which resulted in higher total force. Regular waves will result in maximum of approximately 7,000 kilonewtons, whereas with the focused wave groups, it was possible to simulate events with nearly 16,000 kilonewton impact loads. Kindly note that all the values shown here are scaled up to the prototype scale. When considered the surface similarity parameter, plunging waves result in much higher loads than the surging waves. Two upper plots, plots A and B, compare the lever arm for regular waves and focus wave groups. As we can see, both regular waves and focus wave groups resulted in approximately same lever arm, which is between 7 to 8 meters from the still water level. Figure C and D compares non-normalized lever arm against the deep water wave height. As we can see from those two figures, in both cases, non-normalized lever arm goes down as the wave height increases. So that confirms the lever arm does not increase as we increase the wave height, rather the normalized one decreases. As we illustrate in the bottom left figure, the theoretical lever arm is approximately between 12 to 14 meters, whereas measured lever arm is only between 6 to 8 meters. Even 1 in 2 year storm shows a higher forces than the pre-calculated uplift threshold, and also we observed the force lasts much larger duration. However, later we identify the impact area is closer to the base, therefore those high load does not pose any threat to the lighthouse stability. Force time histories from the small scale model test are very different to those developed for offshore monopiles, for example, the theory of Wincan-Omarasi 2005. Also, different incident wave direction shows different wave layering that is related to the combination of slopes and wave characteristics. Implications of this study is geometry of the rock, bathymetry and topography are crucial for wave loading. Usually existing navigation charts or archive drawing are not sufficient to accurate predictions or accurate modeling. Climate predictions in terms of extreme meteorogenic conditions are extremely necessary to correctly assess the risk of exposed rock lighthouses. More importantly, the world's wave loading might not be from the dominant wave direction, rather it could be an average wave coming from a wrong direction or with a wrong combination of wave properties, and also the slope might create the worst wave loading for these structures. Finally, I would like to thank all my co-workers of this research project and also all the partner institutions, including universities and lighthouse authorities of UK and Ireland. And also, I would like to thank especially for the funding agency EPSRC. Thank you very much.